This is actually a paper not on privacy at all. So this is called On the Power of Randomization in Fair Classification and Representation. So it's a paper on algorithmic fairness. And I need to introduce myself. I'm a graduate student at the University of Waterloo, and I'm an incoming PhD student at Northeastern University. And this work was done during my internship at Microsoft Research in fall 2021 with my supervisor there, Amit Deshpande. And this also appeared in the conference ACM Fact, which took place around a month ago. Okay, so a brief, like since there's a privacy audience, I'll give like a brief introduction to what fairness is and what fair machine learning is. I think, as we all know, algorithmic decision making is like increasingly commonplace. Like even in like it used to make decisions of like high consequence. For example, like recidivism prediction. It's used to filter job applications. It's used to determine whether applicants will get a loan and so on. So how these things basically work is applicants like enter all their features into this software, and the software will basically spit out either accept, reject decision, or will spit out a score number. And decisions are based on this prediction of the software. And it has been observed, like for example, even in popular media and like a lot of research, that these algorithms are actually often unfair. And what I mean by that is that they discriminate unfairly based on sensitive attributes like gender, race, income, and so on. And this talk will focus on unfairness in machine learning based classification tools. And some causes for unfairness in ML based classification tools is that there is less training data on minority groups. And another cause could be that the data itself is biased. So like the data collection is biased, the feature selection is biased, and the data is by itself historically encodes bias. And these are two among like lots of different causes of bias in data. Okay, so I'll formalize. I'll give some definitions of what fairness is. And so you consider the following scenario where we have two groups. One is an advantage group and one is a disadvantage group. The advantage group has 100 people and the disadvantage group has 50 people, and the qualified advantage people are 80 people and the number of qualified disadvantage people are 30 people. And I denote them by A1 and D1. The label 1 represents qualified, and the number of less qualified or unqualified people are A0 and D0, which are 20 and 20 respectively. So arguably the most common notion of fairness is what is called demographic parity. And this basically assumes that we have an equal selection rate across both groups. So if we have like a 50% selection rate for group A, then we also have a 50% selection rate for group B. And this notion is very popular, but it's also problematic because it's easy to satisfy this without maintaining accuracy. And you'll notice this is independent of the ground truth label. As a consequence, there have been other fairness notions proposed, such as equal opportunity, which basically tries to equalize false negative rates across both groups. So the number of people that the algorithm rejects from A1 is the same as the fraction of people that a classifier rejects from A1 is the same as the fraction of people that the classifier rejects in D1. And predictive equality is the same thing, but for false positive rates. Okay, so the problem at hand is the following. So we consider a standard learning setup. We have a data distribution P over X cross Z cross Y, where X is like the feature vector. It's a set of all features of a person, for example, age, income, things like that. Z is the protected attribute. So A stands for advantage, D stands for disadvantage, and Y, it's a binary classification task. So Y is the label set. And we So what is the aim of fair classification? So we have the domain x cross z on the left, and we have this classifier f, which goes from the domain to the label set, and we want to maintain as high predictive accuracy as possible with respect to the underlying distribution P, while also satisfying some fairness constraints. And it is like well known in literature that in general this leads to a loss in accuracy, because once you impose fairness constraints, you shrink your hypothesis class to the class of all fair predictors. And another approach to achieving fairness is what is known as fair representation. So we go from the original data distribution over the original space x cross z to a new distribution over a new representation space x tilde, such that all classifiers over x tilde satisfy fairness. And this is somewhat similar to the synthetic data set notion in differential privacy, where we like a trusted data curator basically takes a data set and sanitizes it and releases it into the wild, into the public, and whatever you do with the data set, you'll still be fair. And so this classifier f from x tilde to 0, 1 is called a derived classifier, and its representation is fair if every such classifier over x tilde is fair. Note that going from x cross z to x tilde while maintaining fairness constraints would lead to a loss in accuracy in general, because you're losing information. So you're making sure that all classifiers satisfy fairness, and so you'll likely lead to a loss in information, and this loss of information will likely lead to a loss in accuracy as well. So expanding a bit on the loss in accuracy, so the fair classifier has a loss in accuracy in the following sense that if we do not consider fairness constraints, the most accurate classifier is the base optimal classifier, which will likely have higher accuracy than the most accurate fair classifier. And for fair representation, the most accurate classifier on x tilde will likely have lower accuracy than the most accurate fair classifier on the original distribution, because we are losing information. And so the question that is studied a lot in fairness is, how do we minimize this accuracy loss? And we actually study, so what I told you up till now was the deterministic classifiers and deterministic representation. So we look at randomized classifiers and representations here, where we basically, instead of deterministically mapping a point from the domain to 0, 1, we flip a possibly biased coin and assign a label that way. And the question is, does randomization help us reduce accuracy loss? And note that when we do not care about fairness, allowing for randomization actually does not help accuracy loss, because when we do not care about fairness, then the most accurate classifier is as the base optimal, which is deterministic, and fair representation is not a problem. But it actually turns out that when we do include fairness constraints, then randomization can help us actually reduce the accuracy loss. Okay, so the contributions are as follows. We characterize, given a data distribution, we characterize the optimal randomized fair classifier on that distribution. And by characterize, I mean like show explicitly how it will look and how to construct it from the data distribution. And there's been a lot of work on characterization, but we refine previous work to demonstrate exactly when randomized classifiers will provide an advantage over deterministic classifiers in accuracy. And we also show how to obtain this optimal classifier via a convex optimization problem. So it's also a piecewise linear function, so it's efficient. And what is probably the more important contribution is we construct optimal randomized fair representations. So there's been a lot of work on represent fair representations in literature. However, most of this work does not provide any theoretical guarantees on how much the accuracy loss would be when we go from the original set to the sanitized data set. And we actually come up with a randomized representation that is provably optimal and that actually suffers no accuracy loss. So we are able to come up with a representation such that we are able to remove all the information that would enable an adversary to be unfair, while also preserving all information that such that a classifier can have as good accuracy as the original data distribution. And I think, yeah, I won't go into it more. I have a poster on Thursday. If you have more questions, you could come talk to me there.